I'd like to talk through example 8.5 from the textbook, which is an example of a collision in two dimensions. So here's how we're going to do conservation of momentum in more than one dimension. If you haven't looked at the problem, you should probably read it over and make sure you get the basic details. But it starts with a mass of 5 kilograms moving to the right, which is ultimately going to end up hitting a smaller mass, which is only 3 kilograms, at rest. And then the two masses are going to bounce off one another and fly off at different angles, one up a little bit above the x-axis and one below. So to start this problem, the first step is going to be to draw the before and after pictures that the author's already done for you. You really can't make a lot of progress on these unless you draw the before and the after picture and clearly show which masses are moving and list what their masses and speeds are if you know them. Additionally, you'll have to put a coordinate system on there. So the authors have selected an x and y coordinate system, with x being the direction that mass A is originally moving and y being perpendicular to that. The reason why we're going to need to have a coordinate system is because to do conservation of momentum in two dimensions, we have to do the idea that the initial momentum equals the final momentum in both dimensions separately. So we start with the idea that the initial momentum and the final momentum are equal as vectors, and break that up into two different statements that are true simultaneously. One is that the x components before and after have to be equal, and the y components before and after have to be equal. Now the book uses initial and final and drips subscripts all over their letters. I prefer the unprimed for before and the primed variable for after, but it doesn't really matter in this case because I'm just going to step through the solution that the authors have presented here. So the first step is to write an expression that gives you the x component of the initial momentum. And that's shown in the first line there. Notice that the x component of initial momentum is all carried by mass A, which is moving, and mass B doesn't have any momentum in the x direction. In fact, it doesn't have any momentum at all because it's stationary. And then the next step is to write a similar expression for the momentum of the two masses after the collision. So here they are both moving. And you can see that for the x component of momentum for mass A, they've taken its mass times its velocity and hit it with a cosine of 30 degrees. That's to select the x component of the velocity. The x component would be the adjacent side in our component finding way. And then in the x component of momentum for mass B, well, we know what its mass is, but the question is to figure out what is the magnitude and direction of mass B's final velocity. So that's left as a variable. They call it v with a subscript b, comma, f, comma, x. That means the velocity of B after the collision, but only the x component. It's presently left simply as an unknown at this stage of the game. Now normally if it were me, I would just proceed and get the y components to just generate equations that are true, but the authors here have selected to go ahead and solve right away for the x component of the velocity. So they take the expression that they had for the initial x component of velocity, the before line, and equate it to the momentum final, that's the after line. So you set those two equal to one another, and I think you could even show the work for this. You can solve it to get the x component of mass B after the collision to be 1.89 meters per second. So all they do is set the before line equal to the after line and solve for the velocity of B after the collision, its x component. So with that done, you can proceed to look at the y components of velocity. So as we did before, you make an expression that is the initial component of the initial y component of the momentum. you can see that in fact there isn't any momentum in the y direction initially. The reason is, although mass A is moving, because of the way the coordinate system was selected, it does not have a y component of velocity. So in fact, the initial momentum in the y direction is simply 0. They could have written that, but they didn't. They just left it as an expression there. And then similarly, write an expression for the y component of momentum after the collision. And so you can see that for the velocity A, they've got the mass of A times the velocity of A, 1.0 meter per second. But then hit it with the sine of 30 degrees. That's to select the y component of velocity for mass A in order to get its y component of momentum. And then for mass B, since we don't know its velocity, that y component of momentum is just left as a variable. And as they did before, all you have to do is equate the before and the after and solve for the y component of momentum. And you can see that the answer, I think you should be able to do the math there yourself too. And if you have some trouble, ask questions. But in any case, the final velocity of mass B, the y component, comes out to be minus 0.83 meters per second. So the minus is interesting because it tells you that mass B is moving at an angle that's below the plus x axis. So the y component is negative. And then the last step should be pretty familiar. If you want to find the magnitude of the velocity of mass B after the collision, since this is a two-dimensional problem, you have to sum the squares of the components and take the square root. So that's what's done in that last step there, resulting in 2.1 meter per second. And then I just scribbled it as nicely as I could here with my little pen tablet. If you want to find the angle of the final velocity of mass B, you got to use a trig function. I selected tan. The tangent of the angle is the y component divided by the x component. I prefer absolute value for these angles so that it comes out to be plus 24 degrees, and then you can just put that in an answer in a sentence form. So you could say that, so if you really wanted to answer this question, you would say after the collision, mass B would be moving at a speed of 2.1 meter per second, directed at an angle which is 24 degrees below the plus x axis.